We are on topic 7, FRQ topic 7. In this topic, we cover rectilinear motion, which is horizontal and vertical motion. This is a topic that we did in the fall, not to be confused with motion along a curve, which we did in the springtime. So that'll be coming up next. If you notice on our little chart here, these questions are not going to be on an FRQ for Calculus BC. For Calculus AB, it's quite normal for them to be on an FRQ. But for the BC exam, they're going to cover motion in parametrics, not in just horizontal and vertical. Where you're going to see these on the BC exam or on multiple choice questions. However, it's the type of questions that we will have, that we ask ourselves whether it's an FRQ or a multiple choice question. So I always include it as one of our topics here. If you need a refresher on motion, I have a document in our notes. You can go back to that unit's notes. It's in there. And I have a comparison between horizontal and vertical and motion along a curve. Okay? I'm not going to go through these, but if you need a refresher on those, it's all right there. Okay? I just want to go ahead and jump in and start doing some problems. So this was from the AB exam in 2016, and this was number 2, so it was with a calculator. Okay? They give us a particle moving along the x-axis, and they give us an equation for the velocity of the particle. And they give us that the particle is at position 2 when time is 4. So I'm going to say x at time 4 is equal to 2. That's an initial condition. Part A, at time 4, is the particle speeding up or slowing down? When we did rectilinear motion, we said that a particle is speeding up when acceleration and velocity have the same sign. Let me write that in here. A and V, same sign, means we're speeding up. A and V, different signs, means we're slowing down. So that's how we did it when we did rectilinear motion in the fall. So I need to find V at time 4, and I need to find A at time 4. And I need to know their signs. Well, V at time 4 is not going to be hard. We just put 4 in for T here. A at time 4, we're going to need to do something to get it. What do we do to get it? We take the derivative of velocity. Now our calculator, it's calculator active, so our calculator can do that for us, but we remember that we have to tell AP what we're doing. Don't just write a number down without saying what you did to get it. So into my calculator, I'm going to put in for y1. I know I'm going to be using this throughout the problem, so I'm going to write my equation for the velocity. If you recall the velocity equations, x prime, y prime, those were always good to put in for y1 and y2. So I do a double check, make sure I put that in correctly. And now V at 4 would just be y1 at 4. So I'm going to say what it is, and then I'm going to say it's positive. All right? A at time 4 would be math 8, the derivative of the velocity at time 4. And I see that it is a negative 1.164, which is negative. So I can say at time 4, the particle is slowing down. Since A at 4 is negative, since A of 4 and V of 4 have different signs. Okay, that's my justification. So this was worth 2 points for the conclusion with reason. Okay, now again, for you guys, this particular question will be a multiple choice, but it's good to know. Good to know the reason, how to write it and stuff. All right, part B. Find all the times in the interval when the particle changes directions and justify your answer. Change in direction. Change in direction is when V changes signs. Remember, when V is positive, we're going to the right. When V is negative, we're going to the left. Or if we were moving on the y-axis, when V is positive, we would be going up, and when V is negative, we would be going down. So change in direction means V changes signs. Okay, so I think I'm going to write that. The particle changes directions when V changes signs. And now I'm going to find out when that is. So I have my equation for velocity in here. I only am interested in 0 to 3. And I have no idea what to make my y min and y max. So I think I'm just going to make it -5 to 5 and go from there. Oh, that was a happy time. So there's only one time that the velocity changes signs, and it's right there. So I'm going to say V is greater than 0 on 0 to second calc 5, enter, enter, enter. Oh, I can't do enter, enter, enter because I don't have a 0 in there. Let me put that in there real quick. Second calc 5, second calc 5, enter, enter, enter. And I get, let's see, 2.707. V is less than 0 on 2.707 to 3. I don't need to include the 0 or the 3. Okay, so the particle changes directions at t equals 2.707. That for the AB test was worth 2 points. 1 point for t is equal to 2.707. 1 point for your justification. Part C, find the position at time 0. I knew this was coming as soon as I saw them give us an initial condition up here. So we're going to set up the fundamental theorem of calculus. So the position at time 4, which they gave us, minus the position at time 0, which we're trying to find, is equal to the integral 0 to 4 of x prime. And x prime is the velocity. So I'm going to say 2, which is x4, minus x of 0 is equal to 0 to 4 of my velocity function. So x of 0 will equal, in my calculator I'm going to be putting in 2 minus that integral, because we're using a little algebra there to get there. So 2 minus the integral 0 to 4 of my velocity. That's why it was so handy to have our velocity function in there in our calculator. So negative 3.815, and that was worth 3 points. 1 point for the integral, 1 point for uses initial condition, and 1 point for our answer. Okay. Part D, find the total distance traveled by the particle. Total distance traveled by the particle. So remember that total distance traveled, total distance is always the integral from 0 to 3 of the speed, right? Well, the speed is the absolute value of the velocity. That's what it is, right? So when we're in parametrics, that is the square root of x prime squared plus y prime squared. That's when we're in parametrics. Well, we're not in parametrics. There's just one component. There's just one component. So it's just the square root of x prime squared, which is the absolute value of x prime, or the absolute value of v. All right? So in my, of course, you wouldn't put this on if this was the AB FRQ. So Math 9, 0 to 3, absolute value. What's a good way to get absolute value? I think it's in F1. We don't use it just a whole lot, but I think it's right there. Okay, it's not there. I'm going to try F2. There it is. It's in F2. That's I know it's in one of those, so I just pick one until I get it there. Of y1 dx. So 5.301. Okay. The other way to do that would be to say Math 9, 0 to 3, the square root of our velocity squared. If you prefer to just remember one formula, you can just do that. And clearly you get the same answer because it's the same thing. Okay? That was worth 2 points. 1 point for the integral, 1 point for the answer. Okay? So that was back in 2016. Let's go take a look at 2019. Let's see what they did in 2019, which was the last, anyway, 2019. All right. So this one I could have put as a data question, right? Because it has this table of values. Could have done that. But as you'll see, there's a lot of velocity and particle position and so forth. So it says the velocity of a particle moving along the x-axis is given by a differentiable function. We may need that. Differential function v sub p, where v sub p, a function of t, is measured in meters per hour, and t is measured in hours. Selected values are shown on the table. Particle P is at the origin at time 0. Okay, so particle P is at the origin at time 0. They gave us an initial condition. So we're moving along the x-axis, so x sub P at time 0 is 0. Okay, I'm saying x sub P because they're giving me v sub P. It tells me that quite likely somewhere in the problem we're going to have some other particle, maybe Q, P and Q. Makes me want to look, and I just glanced down at part C. I haven't done this problem in a long time, and a couple of years, and I just see that they do indeed have a particle Q happening in part C. Okay, part A, justify why there must be at least one time. Okay, as soon as I read that, I think, oh, we're talking IVT or MVT. I just know it. One time between 0.3 and 2.8 such that v sub p prime equals 0. Okay, v sub p prime. So since they give me a prime, I know I'm going to be using the MVT, mean value theorem. So mean value theorem, we must state that the function is continuous on the closed interval and differentiable on the open interval. We must state that. So I take care of that first. So v sub p at of t, v sub p, is given to be differentiable. Is given to be differentiable. So v is differentiable everywhere, not just where we need it, but everywhere. If v is differentiable, it must be continuous. So v sub p is continuous and differentiable. Okay, so that I got my condition out of the way. Now I want to make sure that I do get 0 for my average slope here. That's what mean value theorem is. Instant slope equals average slope. So I want to make sure I get 0 here. So remember what we're doing there. V prime would be change in v over change in time, right? So I always start with where they give me, and since they gave me this interior time interval, I'm thinking that's going to give it to me. So I look up here, and sure enough, the change in v is 0. So I know that's going to work for me. So v sub p at time 2.8 minus v sub p at time 0.3 divided by 2.8 minus 0.3, that's the average v sub p, the average there, that's equal to 55 minus 55 over 2.8 minus 0.3, which is 0. Therefore, there must exist at least one time t between 0.3 and 2.8 such that v sub p prime is 0. That's using the mean value theorem. That was worth 2 points. V sub p minus 2 of 2.8 minus v sub p at 0.3 is 0, and another point for the justification using MVT. Alrighty, part B. Use the trapezoidal sum with 3 subintervals, and they give me the subintervals, to approximate the value of this integral. Okay, well, trapezoidal sum does approximate the value of just the integral, so I don't have to multiply by anything else. It's a trapezoidal sum, so this is the one with the 1/2. So I start with my first subinterval. 0.3 minus 0 is 0.3 times, from 0 to 0.3 I add those two heights, so 0 plus 55, and I'm actually writing 0 plus 55. They need to see both of those heights, alright? Plus, go to our next subinterval, 1.7 minus 0.3, or you can write 1.4 there. For that subinterval, I'm adding those two heights, 55 plus negative 29. Okay, next subinterval is 2.8 minus 1.7. And for that, we'll need the negative 29 plus 55. And that's it. I don't need to get out my calculator. I don't need to do that. This was worth just 1 point. That's interesting. Usually that's worth at least 2 points, but this time they only made that worth 1. Okay, part C. A second particle Q also moves along the x-axis so that its velocity for 0 to 4 is given by this equation, still meters per hour. Find the time interval during which the velocity of particle Q is at least 60 miles per hour. Okay, that doesn't sound very hard. We just need to graph that, right? So this is a calculator active problem. We have not used our calculator yet in this problem, but it is calculator active. So I'm going to put this equation in for y1 carefully. Okay, and we want to see where this is at least 60 miles an hour, so I'm going to put 60 in for y2. And we're given 0 to 4, that's nice. So 0 to 4 for my window. For my y max, I know I need to go bigger than 60, so I think I'm going to go to 100, see what happens. That wasn't bad. Okay. The time interval when the velocity is at least 60 will be from this time including to this time including. So second calc 5, enter, enter, enter. I need to tell AP what I'm doing here. So I'm going to say V sub Q of T is greater than or equal to 60 on, okay, so that time, let me grab that time, 1.866 to second calc 5. Let's get over here a little bit. Enter, enter, enter. And gosh, that's hard to read on there. So 3.519. Okay. All right, so that was that first part. Now we want to find the distance traveled by Q during the interval where Q is at least 60 miles an hour. The velocity is at least 60 miles an hour. So now this is the now this is just an integral. So I'm going from that first time to our second time, and now that I know I'm going to need these exact values, I realize I did not store my first time. But before I forget, I'm going to go store this time in for, I'm going to store that in for B. That's my upper boundary. And now I'm going to have to go back and get that first intersection value again so that I have the entire value. Remember, your final answer has to be correct to 3 decimal places. So you want to make sure you use the complete value until you're finished. Okay? So again, this is going to be the absolute value of V. Or the square root of V squared. Either one. Same answer. So math 9, A to B of the absolute value of my y1. And I get 106.109. This was worth 3 points. 1 point for the interval, 1 point for the definite integral, 1 point for my answer. On to part D. In part D, at time 0, particle Q is at position x equals -90. Okay, so there we're saying x sub q at 0 is -90. Okay, using the result from part B and the function v sub q from part C, approximate the distance between the particles P and Q at time 2.8. All right, so in my mind I'm thinking, okay, we need to find the position of P at 2.8 and the position of Q at 2.8 and see how far apart they are. They're both on the x-axis. So we'll just subtract that. So I'm going to do q first, because I get to use my calculator for that. I have the function for that. So x sub q at time 2.8 minus x sub q at time 0 is the integral 0 to 2.8 of the velocity of q, that's x prime of q, at time t dt. So this gives me x sub q at 2.8 is equal to negative 90. I'm going to bring that over. Negative 90 plus that integral. That's the one I have stored in my y1. So I'm going to go get that. So negative 90 plus math 9, 0 to 2.8 of my y1. So 45.937 dot dot dot. Okay, have that. Now I'm going to do the same thing for particle p. So x sub p at 2.8 minus x sub p at 0 will be the integral 0 to 8 of the x prime of p, which is the velocity of p, right there. Which means x sub p, the position of p at 2.8, will equal my initial position for p, which they gave me as 0. They gave that to me as 0, plus this integral. In that integral, we found an approximation for in part b. So this is a time where we have a choice. We could come up here and put that into our calculator and get our answer, and then use that answer down here. Or I can just say, I don't want to use x because I'm already using x. Let's let maybe let's let y be that integral. So this is approximately equal to y. So the distance between p and q at time 2.8 is the absolute value of y minus that 45.937. I'm just going to give it a couple more decimal places like that. So that would be a safe stop spot for that. This was worth 3 points. 1 point for the integral 0 to 2.8 of v sub q of t. 1 point for the position of q. And then 1 point for the final answer. That's how they scored that. Okay. Now, like I said, you're going to have multiple choice questions on this topic. So I did include, I gave you 2 FRQs to practice, but I also gave a bunch of multiple choice questions for you here. So I thought we'd just go through a couple of these. I have them split up. This first section is with a calculator, and then there's a section for you to do without a calculator. So let's just do a couple of these together. Let's see. 4 is standing out to me, so let's look at number 4. A particle moves along the y-axis so that its velocity at time, so here's its velocity. At what time does the particle reach its highest point? Highest point. So in my mind I'm thinking which might be a good idea to see what velocity is doing. Okay, let's see what the graph of the velocity is doing. So I'm going to put this in. Okay, make sure I got it in there right. And we just have time greater than 0. We don't have an ending for our time. So let's just put in maybe 10 and go from there. And I really don't know what my max and min velocity will be, so I think I'm going to make it -10 to 10, and I can always adjust. Okay, I did not need -10 to 10. I think actually probably -1 to 1 would have worked just fine. Yeah, it sure would. So the velocity is positive from 0 to this time, and then the velocity is negative from this time on, right? So think about that. That means we're on the y-axis. So wherever, I don't know where we start, but wherever we start, the velocity is positive. So we're going up until we get to that time, which isn't too long, and then we go down. So clearly we reach its highest point at that time. So I need to find out what that time is. I don't have 0 in for anything. Let me go get 0 in for that. Second calc 5, enter, enter, enter. And we get the time 0.443. And that's answer choice C. So that's how I would do that problem. And I know I did not write anything down, so you'll have to write yourself some notes there. Let's see what else is standing out to me. I like, because AP likes, they like finding the position of a particle. So let's do that. They give us the velocity. They say the particle is 8 when time is 2. Find the position when time is 5. So that's fundamental theorem. X of 5 minus x of 2 is integral 2 to 5 of x prime, which is v. So x of 5 will be my 8 plus that integral. Little fundamental theorem. So 8 plus integral 2 to 5 of this velocity function dx. 12.371. 12.371, it's on there, so it must be right. Okay, so that was a couple of with a calculator multiple choice questions. Let's go grab a couple without a calculator. Maybe 1 or 2 without a calculator. Okay. Let's see. Let's take a look at number 17. A particle moves along the y-axis again, so that its position at any time from 0 to 5 is given by this. So that's the position. During which intervals is the particle slowing down? Well, slowing down means that A and V have different signs. So I need to get A, I need to get V. We'll get V first, since it's the first derivative. So V of t is the derivative of the position, so that's going to be 4t cubed minus 36t. I'm going to be setting that equal to 0 and solving it for t. A of t is the derivative of the velocity, which is 12t squared minus 36. I'm going to be setting that equal to 0, solving it for t. Here, if I factor out a 4t, I'm going to be left with t squared minus 9. So t will be 0 and plus and minus 3. Here, if I factor out a 12, I'll have t is plus and minus square root of 3. Okay, no calculator. So I am making a number line, and I'm going to put all of these values on my number line. Okay, I'm going to put 0 in the middle. Square root of 3 is less than 3, so I'm going to have square root of 3 and 3. Oh, and I just noticed, I just was reminded of this. So I don't have to do these negatives because I don't care about them. I'm only caring about from 0 to 5. Okay? I'm going to put velocity on top and acceleration on the bottom because I'm doing a sign chart because I need to deal with signs. Okay? All right, let's look at velocity first. For velocity, if I go slightly over 0, this will be positive, this will be negative, correct? So that's negative. And I know it's going to stay negative until I get to 3 because that's the only time that velocity is 0. Now if I go over 3, like a 4, I'll have positive times a positive, so here we're positive. Okay, acceleration. Let's go slightly over 0. Slightly over 0, I'm going to be negative. Okay, slightly under 3. Slightly under 3. Okay, slightly under 3. I am going to be positive because we're squaring this and that's going to make it bigger, right? So this is going to be positive. And then we're going to stay positive because we didn't have any other zeros in there. So the particle is slowing down right here from square root of 3 to 3, like that. Okay. So there were a few multiple choice questions just to get you going, seeing how to think about that. Number 18 is a nice little problem, so see how you do on that. But anyway, these are good. These will show up on the BC multiple choice part of your test.